going to record. So we said, you guys actually sort of worked out yourselves, that potential energy gravitational is due to both position of the object and characteristics of the object. Well, turns out potential energy elastic potential energy is due to the same darn things. And you guys worked it out beautifully. The characteristic piece is the inherent elasticity of the material. The position piece is how far you stretch it. How far, and we're gonna start to use the term deform. When you deform a material, you change its form. And for elastic materials, there are two ways we can deform them. We're going to talk about that in a second. Okay, and this is where we left our physics heroes, saying that elastic potential energy, PEE, depends on deformation. And that, for any given material, that's going to be the factor, is how much you deform the material. When we say deformation, you have seen springs that get stretched out. You have also seen springs that get compressed. Where is some place in everyday life that you interact with springs that do load under compression? Pencils. Yeah, okay, I didn't even think about that one. Pens, ballpoint pens, have a compression spring in them. Cars was the one I was thinking of. The suspension system in cars is a giant, heavy, stiff metal spring that the mass of the car compresses. So, okay. The amount of deformation is the difference between its relaxed length and its compressed or stretched length. So whatever the difference, it's basically a delta X quantity because it's the difference in position. If we have a spring that's relaxed length looks like that, and we stretch it out to look like that, then the amount of deformation is that much. Okay, that's hard to see. Let's move that up. Yeah, that gives us an amount of deformation like this. We refer to the deformation amount as X. So does the formula for elastic potential energy look like anything else to you? PE equals 1/2 kx squared. Kind of looks a lot like kinetic energy, yeah, where kinetic energy is equal to 1/2 mass v squared. A parallel can be drawn. K is a constant. K is actually the spring constant. And there are different spring constants for any, again, I said, those of you who are heading into engineering fields, you will find there are constants of all sorts for all materials, constants of conductivity, constants of thermal expansion and contraction, and constants of elasticity or spring constants. So that spring constant tells you how many newtons of force are generated when you deform that material by a given amount. And the units for spring constant are newtons per meter. A material that had a spring constant of 1, so if K was equal to 1, that would mean that if you deformed that material by an entire meter, you would generate a force when it sprung back of 1 newton. Conversely, it should take a newton of force to deform the material by a meter. So, can you test the spring constant of a material? Yeah, and you're actually going to do a lab. It's kind of like the friction and forces lab, where it's not a build project. It's kind of a challenge lab. It's a bungee jumping lab. You don't get to bungee jump, but you get to design a bungee jump for an object that you have to protect, and you'll figure out the spring constants for a variety of materials. Okay. That K value is specific for every material. Now you might have two materials that have similar K values, but every material has a K value. Oh no, not a good poker face at all. Okay, so stiffer springs generate more force. They store more potential energy. The stiffer the spring, the higher the spring constant. Because, so for a K of 32 newtons per meter versus a K of 2 newtons per meter. This one, if you deform it by a meter, it's going to take you 32 newtons to do it. It's also going to deliver a whap of 32 newtons if it hits you. With this one, it only takes 2 newtons of force to deform it. And if it springs back and hits you, it's only going to deliver 2 newtons of force to you. So the amount of work that it can do is less. Do you want spring scales to sit and think about how much 2 newtons of force is? Okay. Using a spring scale, can you calculate the spring constant of the spring within the scale? Of course you can. Okay, so for your spring scale, if this is the relaxed position where it's reading 0 newtons of force on the spring, and you deform that spring, and that's where the spring is at this position. This is its relaxed position. This is the undeformed position. If you deform it and get it to there, the difference in position, now you would have to, of course, convert that to meters. If this takes 3 newtons of force to deform it by that far, you can actually figure out the spring constant of the spring. So we've got one spring scale for which it takes 5 newtons of force to move it 10 centimeters. What do you, so K equals 5 newtons divided by what? Be careful. There you go. 10 centimeters would actually be 0.1 meters. Oh yeah, that's what you said. What's the spring constant of that spring? $50.
The spring constant of this rubber band is 17.5 newton meters.
17.5 newton meters. Okay. 83 newton meters for the spring scale you've got?
Yeah.
Okay. So if you're going to design a spring scale, what do you need to know? You need to know the spring constant of the spring, and then you can create a scale which will actually tell people, oh, hey, this is how much force you're exerting on it. That's all it is. When you do, and I'm again foreshadowing here, the bungee jump lab probably sometime next week, you will have a variety of materials available to you, and you will have to determine their spring constants and plan for how much you can deform them using the mass that you're given. And maybe we'll see if we can bungee jump things off the balcony here. That would be high stakes.
We should do that like a...
So now that you have looked at the equation, what is it? PEE equals what? 1/2 kx squared. Now we're going to do some practice. And of course, they throw the ugliest possible practice problem at you first, but it's good fodder for discussion, so let's go. We're going to actually take this in 2 parts, and we're going to have a philosophical conversation about how the book handles some things. And mind you, I am a lowly high school physics teacher with a degree in biology. I am not a physicist. Some of the people who wrote and reviewed this book are, but I still have a philosophical beef with them. So we have a stunt person standing on a bridge. The stunt person weighs 70 kilograms. They're on a bungee cord. We'll make our bungee cord red. Has anybody here ever bungee jumped? No? Would anybody here like to bungee jump? Okay.
Those little things like the carnivals where they strap you into the thing and you bounce on the trampoline.
That's similar. That's similar. That's cool. Okay, so the bungee cord has an unstretched length of 15 meters. Oh, and by the way, This person is 50 meters above a body of water.
Oh, no.
So 50 meters is about 200 feet.
Yes.
It's a bridge, I think.
Oh.
So they do it in West Virginia. They do Bridge Day at the New River Gorge, and people bungee jump off the New River Gorge Bridge. I wouldn't do it, but somebody does it. If the fall didn't. Okay, so the unstretched length of this bungee cord, we're told, is 15 meters. When it's all stretched out, it has a length of 44 meters. Spring constant of the bungee cord, so, whoops, K of the bungee is equal to 71.8 newtons per meter. What is the potential energy relative to the surface of the water at the point when the stuntman stops falling? So our little stunt person's gonna be there. So what we want to know is the potential energy total here. PET. Potential energy total, PET, which is the sum of your P and your PEG. So let's handle the elastic potential energy first, okay? Because we just learned that it's fresh, so let's do that. Well, nah. Let's do the PEG first. That's the way I wrote it. That's the first one we learned. Okay. So to find your potential energy due to gravity, we need to know, and we're saying that the surface of the water is our arbitrary 0 point. Would he actually stop when he hit the water surface? No, he'd continue to the bottom of whatever body of water this is, potentially. But we're using the top of the water as surface. Okay, so that's our 0 mark. So how far, what is the distance here? Well, we said this was 50 meters. And we said this was 44 meters, so there's 6 meters between where this stunt person stops and the surface of the water. So we know that PEG is equal to mass, gravity, height. PEG is equal to the stunt mass, which is 70.0 kg. Acceleration due to gravity. Oops. Negative 9.81 meters per, whoops, yep, sorry, I screwed that up. 9.81 meters per second squared. Times the height above the surface, which is 6 meters. So at the point when this person is at the bottom of the bungee cord, we say that they have a potential energy due to gravity of 4,120.2 joules. How many sig figs do we have? 3? Is it 50.0 and 44.0? So 6.00. Well, the 6.0 was my error because they actually give you 50.0 and 44.0. So that would be 60.0. Oh, no, you're right. It wouldn't. It would be 60.0. Because it's addition and subtraction. You can only go as far as the decimal places. So, no. It is 6.0 is the difference.
If we're finding the potential energy total, we wouldn't take the sig figs yet.
Well, we won't for what we're going to add it up for. You're right. If you were giving, good distinction. If you were giving an answer here for the gravitational potential energy, you would take sig figs. if you're using this number to add back in, you would use the whole number. But if we just wanted to talk about this, we would say 4,100 joules for the potential energy due to gravity. Now let me ask you, well, I'll save the question. Okay, so we have, roughly 4,100 joules of potential energy. That's how much work this person's body could do if they fell and hit something. That's how far they would move something. Okay, so it's significant. Yeah, it's not insignificant. And that's 6 meters up, so 6 meters up is like probably the back of our old football stands. Might be 6 meters up. I don't know, something like that. They might have been 5 meters. So that's a serious amount of work that could be done. Okay, so what about the elastic potential energy, the P? Well, 1/2 K x squared. So, how do we get our x? Yeah, it's the difference in the deformed and undeformed length. So we have 15 and 44. Our K was a given of 71.8, so 1/2 times 71.8 Newton meters over 44 minus 15 is 29. Oh, it's in the book. Duh. 29.0 meters. That quantity squared. So 29 squared times 0.5 times 71.8. So the elastic potential energy, we get a raw value of 30,191.9 joules. Awesome. So, what your book would have you do is add those two together for your total potential energy. Let me shrink these both. Philosophical issues with this answer. This was actually probably the first or second year I taught physics. A student said, well, but wait a minute. Shouldn't, what did they say next? This potential gravitational energy, the philosophical issue, that potential energy due to gravity, in what direction could that body do the work if it fell?
Say that again?
Okay, so looking at the potential energy due to gravity. So this person, this stunt person is here. They could fall to here. In what direction would the work be done on an object that they fell on? Down. They'd be falling down 6 meters. So the sort of stored energy they've got from gravity is downward. The potential energy they have from elastic, so they are here, they could end up here. In what direction is that work going to occur? Up. So what this student said to me years ago, and this was, like I said, it was probably my first year teaching physics, and I was just like, okay, I can make it, was, shouldn't those be subtracted? Because they are operating in opposite directions. The potential energy from gravity actually almost the potential energy from elastic kind of cancels out the potential energy from gravity. Now, that is not how your book handles it. I am not wholly comfortable with their handling of it because I think it's a very valid point that, they're really in opposition, and we've been doing all this stuff with, forces up and forces down, work this direction, So I guess the best answer that we came up with after a lot of reflection and thought is this. They're talking about potential energy total, and the word total is really important because they're talking about magnitude. What would be the term you would use if you subtracted them and got the difference? Think back to all the work we've done with net, right? So if you were looking for the net potential energy, you would, and I thought that was a brilliant point, and it was, like I said, it was not me who came up with it, it was a student who, rocked it. The net piece we came up with on reflection and discussion, but that's the difference that I see, but the book doesn't address that, and I think it's an important thing to address. So, okay. Other than that, questions, comments, concerns? Yes?
So when we have like a problem like that,
I would, well, for one thing, I don't typically give problems where we're mixing gravity and elastic. I typically, maybe I should, but I haven't. And that's the distinction that I would use. If we're talking about total, you're talking about the total potential energy, regardless of sign. If you're talking about net, we want to actually know how much work this thing could do. So I think that's reasonable. And, those of you who are going off to physics, please, 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 at some point encounter this problem and come back to me and tell me things. I've had students do that. It's great. I had a student who came back and told me we were wrong on a project, and I said, I know, I figured that out. Now tell me how to get it right. So, okay, 4 minutes. We'll come back, and you can work on 4D. That'd be 5D, not 4D, not to give anybody horrible flashbacks. Sorry. Okay, so assigned with the practice 5D problems, numbers 1 through 3, page 180.